In this video, we only set up the integrals to find the surface area. The function given can be in terms of x or y, and the axis of rotation can be either x or y. Now, recall that the surface area is 2 pi, the integral of the radius times the arc length. So that is the circumference times the arc length. About the x-axis, the radius is y, and if we were to rotate about the y-axis, then the radius is the distance x. The arc length can be either in terms of dx dy or dy dx. So the arc length is the square root of 1 plus dy over dx squared dx, or the square root of 1 plus dx over dy squared dy. For example, A. Y is given in terms of x, and so it's square root of 2x minus x squared. X go from 0.5 to 1.5, and we rotate the curve about the x-axis to form a surface. The radius is therefore y, because we rotate about the x-axis. Y is a function of x, and so we would find dy dx. The derivative of y with respect to x is 1 over 2, the square root of 2x minus x squared, times 2 minus 2x because of the chain rule. That is 2 minus 2x over 2, the square root of 2x minus x squared. We factor out 2 in the numerator to cancel out the 2, so the numerator is now 1 minus x. And in the arc length formula, we would need to square dy dx. So square 1 minus x in the numerator. And in the denominator, the square root of the square canceled out. Also in the arc length formula, we would need to add 1 to the square of the derivative. And so 1 plus 1 minus x squared over 2x minus x squared. The common denominator is 2x minus x squared. And so we would multiply 1 over 1 to 2x minus x squared so that we can combine both terms. Expanding 1 minus x squared, we have 1 minus 2x plus x squared. But 2x minus 2x is 0, and minus x squared plus x squared is 0. And so the numerator ends up with 1 only. The denominator is still 2x minus x squared. The surface area is therefore the integral. Notice that we found dy over dx. That means the variable of integration is x. So x goes from 0.5 to 1.5. So 2 pi times the radius is y, times the arc length, but the arc length is the square root of 1 over 2x minus x squared. Always simplifying the argument of the square root before we plug it into the formula. 2 pi is a constant multiple. We can move it to the front of the integral. Y is given in terms of x, the square root of 2x minus x squared. The square root of 1 is 1 over the square root of 2x minus x squared. But, so the square root of 2x minus x squared canceled out. And so we end up with 2 pi, the integral from 0.5 to 1.5 dx. So not only we set up the integral, but we simplified it. Okay, so the second example, now x is given in terms of y. Y is 2, the square root of 4 minus y, and y go from 0 to 15 over 4. We rotate the curve about the y-axis. And so if we rotate about the y-axis, the radius is x. Y go from 0 to 15 over 4. And so we would want to integrate from 0 to 15 over 4. X is given in terms of y, so we would find the derivative of x with respect to y, which is 2 over the derivative of the square root of 4 minus y is 1 over 2 root 4 minus y. And then we multiply -1 because of the chain rule. 2 cancel 2. We have -1 over the square root of 4 minus y. In the arc length formula, we would need to square the derivative. And so dx over dy squared is 1 over 4 minus y. And then we need to add 1 to the square of the derivative. And so 1 plus dx over dy squared is 1 plus 1 over 4 minus y. So that is 4 minus y plus 1 over 4 minus y. 4 minus y is the common denominator. The numerator is now 5 minus y. The denominator is 4 minus y. Now this is the argument underneath the square root. The square root of 1 plus dx over dy squared is now the square root of 5 minus y over 4 minus y. Now using the surface area, it is the integral of 2 pi times the radius, but the radius is x in this case because we rotated about the y-axis. The lower limit of integration is 0 and the upper limit of integration is 15 over 4. The arc length is the square root of 1 plus dx over dy squared. But remember, we simplified this earlier. The variable of integration is y, and so we would need to rewrite x in terms of y. But x is given at 2 the square root of 4 minus y, and so we just simply substitute x with 2 the square root of 4 minus y. The arc length is the square root of 5 minus y over 4 minus y. And then don't forget dy. The constant multiple of 2 pi times 2 is 4 pi. Integrate from 0 to 15 over 4. The square root of 4 minus y canceled out, so we end up with the square root of 5 minus y dy. For c, x is given in terms of y. X is 1/2 e to the y plus e to the negative y, and y go from 0 to ln of 2. And since we rotate about the y-axis, the radius is x. But we recognize that 1/2 e to the y plus e to the negative y is actually the definition of hyperbolic cosine. And so dx dy is hyperbolic sine of y. And then when we square it, we have the square of hyperbolic sine y. And then in the arc length formula, we need to add 1 to the square of the derivative. And so 1 plus hyperbolic sine square y. But using the hyperbolic identity, this is actually hyperbolic cosine squared of y. So 1 plus dx dy squared is hyperbolic cosine squared of y. And taking the square root of this, we end up with hyperbolic cosine of y. And so the arc length is just simply hyperbolic cosine of y. The surface area is 2 pi. The integral goes from 0 to ln of 2 along the y-axis. The radius is x, and the arc length ds. But x is given in terms of y, specifically hyperbolic cosine of y. And so we replace x with hyperbolic cosine of y. The arc length is the square root, but we simplify this already, which is hyperbolic cosine of y. and then dy. Simplifying the integrand, we have hyperbolic cosine of y squared. We can just leave the answer in this form, but we can also rewrite it in terms of exponential function. Hyperbolic cosine of y is e to the y plus e to the negative y over 2. We circle back to the original expression x equals cosine of y, which is 1/2 e to the y plus e to the negative y.